Sorry, I don't hear you quite well, but yeah, thank you very much for the introduction and thank you for the invitation to speak. Yeah, in this talk, I want to talk about the theorem, which is basically the title of the talk. So I want to show you that every non-trivial, strongly quasi-positive knot is concordant to infinitely many of those. So to infinitely many strongly quasi-positive knots, which are pairwise non-isotopic. And so first I want to start with some definitions and like introduce to you knots and concordance and also strongly quasi-positive knots. And then I want to give you some context on the results, like tell you some related results and conjectures. And in the end, I want to sketch a proof of the theorem. So yeah, feel free to interrupt me anytime if you have any questions. I hope I will hear them well. Yeah, and it's also like it's been a while since I've given a slide talk, so it might be that I'm going a bit too fast. Let me know if I'm too fast. Okay, so let's start with some knot theory and concordance. So throughout the talk, we will work in the smooth category. And a link for me is a non-empty, oriented, closed, and smooth one-dimensional submanifold of S3. You can think of links as living in R3. S3 is just a one-point compactification of S3. And we study links usually up to ambient isotopy, so up to orientation preserving diffeomorphisms of S3. And a knot is just a link with only one connected component. And I've drawn some examples for you. So the easiest knot is the unknot, and up to this notion of isotopy, it's the same as this knot and the other knot that I've drawn. And then here are some other knots, and I could draw infinitely many for you. Yeah, and so in this talk, I want to study knots up to another equivalence relation, which is knot concordance. And so, well, the definition is that two knots K and J, they are called concordant if there exists a smoothly and properly embedded annulus, A, so it's orientation preservingly diffeomorphic to S1 times 0, 1, inside of S3 times 0, 1, such that the boundary of this annulus is a copy of K times 0 union J times 1. And then there's like some orientation issue that we should think about, but I don't really want to think about orientations in this talk. So a schematic of this situation is here on the right-hand side. So this box depicts S3 times 0, 1. And inside, like on the bottom, we have a copy of S3. And on the top, we have a copy of S3. And inside these two copies, we have the knots K and J. And then a concordance between them is this embedded annulus, which co-bounds K and J. Okay, and so this knot concordance is an equivalence relation. And in fact, it turns the set of knots or the set of isotopy classes of knots into a group together with like the group operation of connected sum, which is not so important for this talk, but yeah, so basically a connected sum of two knots K and J as is defined as in this picture. So you choose two arcs and you cut them open and like re-glue differently to form like a new knot. Okay, and this group is quite mysterious. So we don't know the isomorphism type of this group, and there are many questions that are still open about the group called the concordance group. Yeah. So from the definitions, you might have noticed, or it's not so hard to see that isotopic knots are also concordant. But the other way around in general is not true. So if I have two knots that are concordant, it's not usually or often they are not isotopic. And an example of this is that any non-trivial knot which is not slice, so not concordant to the unknot. And with non-trivial here, I mean not isotopic to the unknot, to this like simple boring knot. Okay, and a very famous example is the Conway knot. It was shown by Lisa Piccirillo in 2020, and it's an annals paper that the Conway knot is not slice. So it can actually be a very hard question. So like for this specific knot, it was open for like about 50 years. So it can be a very hard question to determine whether or not it's slice, and more generally to determine concordance classes of knots. Okay, so that's the quick introduction to knots and concordance. Do you have any questions so far? Okay, so I will continue with strongly quasi-positive knots. So it's a theorem by Alexander that any knot is the closure of an n braid for some n greater than or equal to 2. And there's a presentation for the braid group on n strands, which was given by Artin in 1925. And it's the following. So the braid group is generated by the n-1 generators sigma 1 through sigma n-1. And the relations in this group are that sigma I plus 1, sigma I is equal to sigma I plus 1, sigma I plus 1. And also sigma j is equal to sigma j, sigma I, if you know, yeah, if I and j are more than 1 apart. So this is an algebraic presentation of the braid group. And geometrically, what you can think of is that, so a braid is basically a collection of n strands that collect a distinguished set of n points in the space to another set of distinguished points. And they are oriented, and we study them also up to isotopy. So for example, the braid group on 2 strands is just a group generated by this crossing of 2 strands. And and like in the inverse of this would be if I have like the crossing which goes the other way around. And so this is like just isomorph to the integers. The braid group on 3 strands is a bit more interesting. So there we have the 2 generators. So this generator sigma 1, where the first 2 strands cross once, and sigma 2, where the second 2 strands cross once. And there's one relation, which is called the braid relation, that sigma 1, sigma 2, sigma 1 is equal to sigma 2, sigma 1, sigma 2. And like, so I hope you see that, well, I hope you see that like really these 2 pictures are the same up to isotopy. You drag the green strand over the blue strand. And so I guess you see where this goes. So like for larger n, we have like more generators and more relations. In particular, for like starting from n greater than or equal to 4, we have like this additional relation that generators which are far enough apart, they commute. So for example here, sigma 1, sigma 3 is equal to sigma 3, sigma 1, and so on. And well, now the theorem of Alexander says that any knot appears as the closure of such a braid. And well, I've drawn a schematic for you what this means. So on the left-hand side, we have this box beta, where beta stands for any n braid in the braid group on n strands. And then taking the closure means that we glue these n strands here on the top to the n strands on the bottom to obtain a knot or a link. And this is called the closure of beta. Now, strongly quasi-positive braids are like a special case of what is called quasi-positive braids. So let me first define those. So a braid beta in Bn is called quasi-positive if it can be written as a product of conjugates of positive generators of the braid group. So it's a product of conjugates of sigma ik's, where ik are like just sum of 1 through n minus 1. And these omega k's, so the words with which we conjugate are just some words in the braid group. And for strongly quasi-positive braids, it's like a similar definition, but we restrict ourselves to certain conjugates of these positive generators. So a braid is called strongly quasi-positive if it's the product of sigma ik jk for some ik less than jk, where now sigma ij is, as I said, a certain conjugate of the positive generator sigma j minus 1 of the braid group. And the generator, the conjugate that we want is that, well, like this long word. So it's sigma I times and so on, sigma j minus 2, sigma j minus 1, and then sigma I, sigma j minus 2 inverse. And what this looks like in terms of geometric pictures of braids is that we have the ith and the jth strand, and they cross once, as for like the other generators, but now like they cross in the front of all the other strands in between. So in front of strand, the I plus first strand up to the j minus first strand. Okay, and I will call this a positive band. Yeah, so these are quasi-positive and strongly quasi-positive braids, and then we call a knot or a link strongly quasi-positive or quasi-positive if it's the closure of such a braid. And well, we see a bit later that quasi-positive braids appear sort of naturally in algebraic geometry. For now, these are like just well, very algebraic definitions. But there are some nice properties about strongly quasi-positive braids with which I want to continue. So yeah, so here's an example of a strongly quasi-positive braid. So the braid sigma 1 squared, sigma 1, sigma 2, sigma 1 inverse, sigma 2. This is a braid in the braid group on 3 strands. And you see that this word sigma 1, sigma 2, sigma 1 inverse is actually the same as this generator sigma 1, 3 in the notation I had before. And I've drawn this braid for you here on the left-hand side. So we have twice the first 2 strands cross each other. This is the sigma 1 squared. And then we have, like here I have sigma 1, sigma 2, and then sigma 1 inverse, and another generator sigma 2. And this is actually, so the closure of this braid is a knot, and it's actually 5-2 in Rolfen's knot table. And now the nice thing about this strongly quasi-positive braid representation is that there's a nice ciphered surface associated to the braid word, which I have drawn here on the right-hand side. So it consists of 3 disks, like these 3 disks, which correspond to the 3 strands of the braid. And then for each of the 4 generators that we have in the braid word, so sigma 1, sigma 1, sigma 1, 3, and sigma 2, I have like a band which connects the disks. And this is true more generally. So for any strongly quasi-positive braid, which I can write as a product of these generators sigma ik jk, there's a canonical ciphered surface associated to this strongly quasi-positive braidword, and we can I guess you see that it's easy to compute the Euler characteristic and the genus of the surface actually from the braidword that we started with. And now it's like a it's a very nice fact about strongly quasi-positive knots and links that this canonical Seifert surface associated to the strongly quasi-positive braidword actually realizes the minimal genus of any surface bounding the strongly quasi-positive knot. So this is the so-called Slice-Benke inequality. It's called inequality because actually they showed an inequality, and then the equality becomes clear if you really look at the specific surfaces. So the statement here is that if we have a strongly quasi-positive braid on n strands and its closure is a knot, then the genus of the knot is equal to the 4 genus of the knot, and it's realized by the genus of this canonical Seifert surface associated to beta, where so the genus of a knot is the minimal genus of a surface, which is an oriented compact connected surface in S3 with oriented boundary the knot K. And the 4 genus is basically the same, but we allow our surface to lie in B4, the 4 ball bounded by the free sphere. And so this is a schematic. And this was shown by Benke in 83 for the 3-dimensional version, and by Rudolph in 93 for the 4-dimensional version, building on work of Kronheim and Rovka. And the last thing that I've written here is that, well, you can actually like in the example, you can compute the genus of the surface from the rive of beta minus n plus 1/2, where this rive is the exponent sum of the braidword. So maybe I will quickly go back to this example. So we have this Seifert surface f of beta here, which consists of 3 disks and 4 bands. And so the surface deformation vertex on a graph with 3 vertices and 4 edges between them. So the Euler characteristic is really 3 minus 4, so minus 1, and from that you can compute the genus to be 1. And and on all this, in this example, is true in more general. This is what Slice-Benke says. Okay, so I defined concordance for you and strongly quasi-positive knots. So I can restate my theorem, and I hope that it makes a bit more sense now. So the theorem is that every non-trivial, so not the unknot, strongly quasi-positive knot is concordant to infinitely many strongly quasi-positive knots, which are pairwise non-isotopic. And I don't really want to talk about links in this talk, but the theorem is true if I replace not by links. And you might wonder, why is it not true for the unknot? Why do I have to assume non-trivial? Well, it's not true for the unknot because the unknot is actually the only strongly quasi-positive knot concordant to itself. And this you can see also using this Slice-Benke inequality. So the 4 genus that appears in the Slice-Benke inequality is a concordance invariant, and the unknot is the only knot with genus 0, and so there's only the unknot, which is a strongly quasi-positive knot concordant to the unknot, or slice, the only slice strongly quasi-positive knot. Okay, so this is about the non-triviality assumption. Now, yeah, I want to give you some context, talk a bit about some related results. So there's like, yeah, I want to show to you like a large set of inclusions of different types of classes of knots. Well, and so maybe we start on the right hand side. So on the right hand side, we have these quasi-positive knots, and I claim that they appear in different settings as well. So quasi-positive knots were shown by Rudolph and Boileau and Orevkov to be those knots that arise as transverse intersections of complex algebraic plane curves with spheres in C2. And the strongly quasi-positive knots, they're like we have seen from the braid theoretic definition that they are like a subset of the quasi-positive knots. And actually like all these inclusions are strict. And now two other classes of knots that are subsets of strongly quasi-positive knots are the positive knots and the algebraic knots. So maybe I want to start with the algebraic knots. So algebraic knots, they are also intersections of complex algebraic plane curves, but now we want to intersect with spheres in C2 that are centered at isolated singularities of these algebraic plane curves. And the torus knots are an example of these knots. So if we take the complex polynomial f of x and y, which is x to the p plus y to the q, and we take the zero set of this polynomial and intersect with the standard S3 around the origin in C2, then we actually get a knot. If P and Q are co-prime, we get a knot. And this is the torus knot TPQ, which you can which is the knot that you can draw on the surface of a solid torus in which winds around P times in the meridional direction and Q times in the longitudinal direction, and which is also like the closure, which is also the closure of this braid here. So sigma 1 through sigma P minus 1 to the Q, a braid on P strands. Okay, so well, why do I tell you about all these classes of knots? So well, a few minutes ago, I told you that isotopy implies concordance in general, and concordance does not imply isotopy in some cases, but it does imply concordance does imply isotopy for this class of algebraic knots. So, and the same is not so. And for this a bit bigger class of positive knots, we have like a sort of similar result, which tells us that, okay, wait, sorry. Maybe I should say this first. So, so Litherland in 79 showed that concordance implies isotopy for algebraic knots. And the way to reformulate this is that we can say that every concordance class in this concordance group that I defined for you contains at most one algebraic knot. Now, we don't know whether this is true for positive knots, but what we do know is that every concordance class in the concordance group contains at most finitely many positive knots. And this was shown by Bade, Dehonois, and Lichty in 2017. Okay, so yeah, as I said, well, it is an open question whether even like the stronger statement that concordance implies isotopy is true for positive knots, and even for like, so there's another subset of knots that I haven't written here, but that I could write. So there's the positive braid knots, which is a set, so which are those knots that arise as closures of positive braids. So we have products of only the positive generators in the braid group. And so they lie here in between. And so for those, we don't know whether, I mean, it could be true that concordance implies isotopy also for these knots. And so, I mean, basically what my theorem says is that a very different type of statement is true for strongly quasi-positive knots, because for those, we show that if there's a strongly quasi-positive knot in a concordance class, then there are in fact infinitely many strongly quasi-positive knots in that concordance class. Okay. Do you have any questions about these sets of inclusions or the theorems? Okay, great. Yeah, and okay, yeah. Well, maybe I should have said so. Yeah, positive knots are those knots that admit a diagram where we only have, okay, I'm not sure if you see my, that admit a diagram where we have only like this type of crossing that I've drawn now, and not like the other type of crossing. So this is not allowed. Okay. Okay, so like in general in my PhD, I'm interested in this question. So does concordance imply isotopy for positive braid knots? And another reason why one could expect this to be true is a conjecture by Ken Baker from 2016. And so he conjectured that concordance implies isotopy for the class of strongly quasi-positive fibered knots. So a knot is called fibered if the complement of the knot is a locally, well, so let me write this, if there exists a locally trivial fiber bundle of the complement of the knot over the circle S1, where each fiber is the interior of some oriented surface with boundary the knot. And so, well, so Baker conjectured that for this class of strongly quasi-positive fibered knots, we have concordance implies isotopy. And the reason why he conjectured this is the following theorem, which he could show, namely that if his conjecture is false, then the so-called slice ribbon conjecture is false. Okay, what is the slice ribbon conjecture? It goes back to a question by Fox from 62, and it asserts that every slice knot, so every knot which is concordant to the unknot, is ribbon. So it bounds an immersed disk with only ribbon singularities. So yeah, I've drawn an example for you here of a ribbon knot. So basically we want that, well, so we want that a knot K is ribbon if it bounds a disk, and the disk is immersed in S3 and has only certain types of singularities. So we want that the self-intersections of this disk, arcs of self-intersections, have like as a pre-image something like this, like two arcs, one of which is in the interior and one of which goes from the boundary to the boundary. Okay, and like you see that this knot here on the right-hand side bounds a disk with these type of singularities. So like this band here is really like the ribbon disk. Okay, and this is like, yeah, it's an open question for 60 years now, whether every slice knot is ribbon. And Baker showed that, well, if we find a counterexample to his conjecture, so if we find concordant, strongly quasi-positive fibered knots that are not isotopic, then we also have a counterexample to this conjecture that goes back to Fox. Okay. Yeah, I guess. I don't know. Yeah. I'm a bit too fast. So do you have any questions for me?
I mean, I guess I can ask the obvious question is, are any of your examples fibered? Can you just prove slice ribbon?
No. Yeah, my examples are not fibered, unfortunately. Well, the reason is that, yeah, I think we can go back to this question later in the sketch of the proof. So basically, yeah, one can see from like a computation of the fundamental group of the complement of my knots that they are not fibered because the fundamental group is free. But yeah, I mean, it would be wonderful to have fibered such examples, but yeah, they're not fibered. And yeah, we can go back to this and it will be easier to see maybe. Yeah, other questions? Okay, well, if not, I will sketch the proof of the theorem. So let me first remind you of the theorem. So the theorem says that every non-trivial strongly quasi-positive knot is concordant to infinitely many pairwise non-isotopic strongly quasi-positive knots. And well, so to show this, we will start with a strongly quasi-positive knot that is non-trivial, so not isotopic to the unknot. And we will start with a ciphered surface for that knot, which corresponds to a strongly quasi-positive braid beta with closure the knot K. Okay. And now I will do like a certain operation on this ciphered surface f of beta, which will change f of beta to another surface f prime. And this f prime will have as boundary a knot, which will turn out to be concordant, but not isotopic to this knot K that we started with. So this is like the very rough sketch. Okay, so let's be a bit more specific. So, okay, maybe I want to show this picture first. So f of beta is the canonical surface associated to beta, and it looks like this surface here that I've drawn on the left. Well, so like in general, we have seen that these quasi-positive ciphered surfaces, they consist of disks and then these some bands connecting these disks, like something like this. Okay, maybe. Okay. And now we will choose like one positive band of this surface f of beta that we like. And what we will do is the following operation. So we will consider a second quasi-positive ciphered surface, which I've drawn here. And I will explain a bit more about this. But now what we will do is like we take one positive band of f of beta and one positive band of this other Seifert surface. Let's call it f of alpha for now. And we will cut open these two bands and reglue, as in this picture that I've drawn here on the right-hand side. Okay, so we change locally only like a very small part of the two Seifert surfaces. And what happens is that, well, I hope you see that from like this picture here to this picture down here, nothing really happened. So I just took this band to this other band, and then again, like going to the next picture, nothing really happened. So, well, actually, like this kink that I have in the surface f of alpha basically cancels with like this band going around like this. So we get this picture here on the right hand side where we started with a surface f of beta with this sort of band, and then doing this operation with another surface where we have like a knot C tied into this band, it results in another, well, okay, so I should write. So this is the surface f prime that we get in the end is the same as f of beta, but with this knot C tied into the one positive band that we fixed in the beginning. Okay, so maybe a bit more formally, or like in words, what we do is, so we, it's a bit unfortunate that we, okay. What we do is we tie a certain knot C into a positive band of f of beta, into this positive band f of beta, to obtain another surface f prime. And now there's like, well, there are some assumptions on this knot C that we need later on. So we want the knot C to be non-trivial, and we want it to be sliced, so concordant to the unknot. And we also wanted to have, maximal Thurston-Bennequin number equal to -1. I don't want to say too much about this, but yeah, it's like, it's an invariant from contact geometry. And well, the key thing here is that there exists such a knot. So there exists a slice knot, which is not isotopic to the unknot and has TB -1. And for example, or like the easiest in terms of crossing numbers is the mirror of the 946. And I've drawn, like, in case you know what it means, I've drawn for you a Lechandrian representative of this, which shows that TB is actually equal to -1. And yeah, so to sum up, so far, we started with a quasi-positive surface f of beta, and we looked at another quasi-positive surface f of alpha, which is actually the annulus of type C. So it's an annulus that follows this knot C, and I've only drawn a schematic of this with -1 twist. So because of this kink here, it's like an annulus of type -1 twists. If like without the annulus, it would be 0 twists and so on. And the -1 here is really the same as the Thurston-Bennequin number, and that will play a role a bit later on. Okay, so we do this operation, and we see that the result of this operation is the surface f prime, which has the knot C tied into one of the bands of f of beta. And now it turns out that then the boundary of the surface f prime is really a knot which is a satellite knot with pattern the boundary of the knot we started with, the boundary of the surface we started with, so the boundary of with pattern the knot we started with, and companion this knot C that we tie into the band. So let me recall about satellite operations. So basically what we have is like we have a solid torus that I've drawn in green here, and we have a knot inside the solid torus. So in this case, the knot is the boundary of f of beta, so just the knot k we started with. And now a satellite operation means that we identify this solid torus as 1 times d2. So with a tubular neighborhood of the companion in the satellite operation, so with C in this case. And so this gives us a new knot inside this tubular neighborhood of C. And this is what we call the satellite with pattern. The satellite with this specific pattern and companion, the knot C. Okay. Why is this, or how does this help us, this observation? There are now 2 facts about satellite operations that are very important for our construction. The first one is that if C and U are concordant, which is the case for us because we chose a slice knot, then the patterns at the satellite knots with the same pattern, but companion C and companion U respectively, they will be concordant as well. So concordance of the companions implies concordance of the satellite knots. And this, in our case, this means that the boundary of the resulting surface f prime will be concordant to the boundary of the surface we started with, the knot we started with. And the other important fact is that since the knots C and U are not isotopic, the satellite knots with companion C and companion U will not be isotopic either. And this is like the very technical part of the article. So this uses a result of Kono and Motegi. And for this, to apply this result, we need that the geometric winding number of our pattern is greater than 1. So I said before, like the pattern is like this, it's the boundary of the surface f of beta that I've drawn here, that I've drawn here for you. And the geometric winding number is the number of intersections of the pattern with a meridional disk of the solid torus. And in this case, we have like two intersections because, it looks like this band that follows the torus. And it's very important that it's actually 2 and not 0 or 1. And and for this, we also need the non-triviality assumption of the knot we started with, so of the pattern that we use. Okay. So we start with a knot and a surface for it. We tie a knot C into the surface and we get another surface, but this other surface has as boundary a knot which is concordant, not isotopic to the knot we started with. Now for the theorem, we need that the knot that we get is still strongly quasi-positive. And this basically follows from the fact that this annulus of type C with -1 twists is a quasi-positive surface as well. And this is something that Rudolf is observed. So a lot of the work about strongly quasi-positive and quasi-positive knots was is by Rudolph. And in this case, well, I will just do like a proof by picture. So basically what happens is that we have we have our surface f of beta here, and you can ignore the gamma, the red curve. And we have the other surface f of alpha, which is the annulus of type C. And here I've really drawn it specifically, not only as a schematic. And again, what we do is like we replace these two bands by two other bands to connect the two surfaces. And now from this picture here on the right hand side to this picture on the bottom left, I hope you see that this is also like just an isotopy. So we take this blue band and the black part of the disk and like extend it a bit to the bottom and the top respectively. And then from this third picture to the fourth picture, I simply extended all these black disks and blue disks to the top and to the bottom respectively. And so like we started with a quasi-positive surface f of beta, so a surface which consists of like disks and embedded bands, positive bands between them. And we also get a quasi-positive surface which again has like these disks and embedded bands between them. So the resulting surface is strongly quasi-positive, and the knot that it bounds is a strongly quasi-positive knot. And then like just what we need to do to finish the proof is that we iterate. Oops, sorry, now we iterate this construction. So we do this operation on the surface, bounding our knot again and again. And each time we get another knot, which is again strongly quasi-positive and concordant to the knot we started with, but not isotopic. So in this case, we get an infinite family of such knots that are concordant but not isotopic to the knot we started with. And of course, it's like a bit of work to show that they are actually, in the end, pairwise not all pairwise not isotopic. And I also said that like all this extends to links. So there's also some work to do if we replace knots by links, but actually the the knot case is a bit more technical. And yeah, so yeah, but okay, but this finishes the proof. So we iterate the construction and we obtain an infinite family, and this is how the theorem is proven. Yeah, thank you very much for your attention.
Are there any questions? So, I mean, you said that you used the knot 946, but presumably there are other slice knots with Thurston-Bennequin -1, and I presume those will likely also different things.
Sorry, say again, the last part I didn't quite hear. It's like,
so you used 946 to tie in, tied in 946 to change your knot. But I assume there are other slice knots as well with the same properties, and presumably those also, proof also works with those.
Yeah, I mean that's right. Like basically the whole article works also if I choose another knot with these properties. The thing is, I mean, yeah, basically it's just for like making pictures and the proof easier that I choose this knot. Like, yeah, I think it's basically for this picture that it's easier, like, because I need to work with this annulus of type does not C, and it's with Thurston-Bennequin number twists, and yeah, it's easier to draw this if I have like a specific knot, but like all the rest of the argument goes through. Like there's no other assumption on the mirror of 946 that I need for the proof to work.
So yeah, I have a question. You mentioned that the Bader-de Hornoy-Liechti result that for positive knots, there are only finitely many in a given concordance class. So I'm just wondering, you go from positive to strongly quasi-positive. So obviously you're constructing infinitely many in the strongly quasi-positive, but what goes wrong with the Bader-de Hornoy-Liechti argument for strongly quasi-positive case?
Yeah, good question. So what Bader-de-Hornoy and Liechti use is like a bound on the signature in terms of the first Betti number of a knot, and which works for positive knots. And but I guess I haven't really tried, but like yeah, I think the reason it would like okay, so I think that like their argument is like a diagrammatic argument, and positive knots are nice because you can like encode them because you have a diagram where you know that all crossings are positive. And for like for strongly quasi-positive knots, you could have a diagram which is not the diagram coming from a strongly quasi-positive braid. And so it's not that easy to say something about strongly quasi-positive braids and knots in that sense. But I have to say I'm not entirely sure what goes wrong with this signature now at the moment. Yeah.
Okay.
Sorry.
A slightly more speculative question is, although you know that these concordance classes have infinitely many strongly quasi-positive knots in them, do you think there's any chance that there might be a distinguished representative, some nice element that's minimal in some sense?
That's a good question. Like, well, so like, I think from my construction, so I haven't proven it, but I think it should be true that like the braid index increases whenever I iterate the construction. So I mean, in the picture, it looks very much like that. And also, yeah, so I would, so I would say like in my construction, the easiest knot is the one that I start with. But well, I mean, if you start with a very complicated strongly quasi-positive knot, and then there could, yeah, then there's like could be an easy. Okay, I guess you could take like the one with the smallest braid index in the concordance class, and but that's not necessary. That's not a unique knot. But you could like so from the Thurston-Bennequin inequality, you know that so starting with a strongly quasi-positive knot, which has a certain genus, I know that all the other knots in the same concordance class will have the same genus, so we'll fulfill this equality. And so if I take the one with the smallest braid index n, I only have like, I mean, I know the value of the rife, and then I can like give a combinatorial description of all the knots that can be in the same concordance class. But I would say these are already infinitely many, so it's not clear to me what would be the easiest.
They're really infinitely many.
Isn't
the rife just counting the number of sort of conjugates, positive generated?
Yeah. I mean, okay, so the rife tells us the number of bands. Yeah, maybe there's finitely many. Oh yeah, because yeah, okay. So we have you're right. Like there's a finite way to encode it. Like I mean, the bands start at one of the disks, and I mean, there's only so many possibilities for a band. So there's a way to encode it. Yeah, I don't know.
It might be
Maybe
hard
one
to
should
tell.
introduce the nicest representative.
Yeah, it might be hard to tell that they all give distinct classes or something. Anyway, are there any other questions? Well, in that case, let's thank Paula again.
Thank you.